Recall the general form of the quadratic equation. It's expressed by f of x is equal to a times x squared plus bx plus c, where we have the restriction that a cannot equal 0 and b and c can be any real numbers. Previously, we've discussed solving for the quadratic equation when it is equal to 0 in order to find the x-intercepts. Below, we're going to look at the vertex form of the quadratic equation in order to solve for the vertex of a parabola. The vertex form, also known as standard form in some texts, including the OpenStax textbook that we use in this course, is given by f of x is equal to a multiplied by x minus p squared plus q. This form is called the vertex form because we can find the vertex directly from the form of this equation. The vertex is given by PQ. The vertex PQ will either be a minimum or a maximum point, depending on whether or not the parabola opens up or down. The direction of opening all depends on the constant a, which is out front of our x term. If a is greater than 0, then our parabola opens up and we have a minimum. So when a is greater than 0, our function will look something like this, and we'll have a minimum value at the vertex. Whereas when a is less than 0, our parabola will open down and we have a maximum value at the vertex. So that is either the highest or lowest value of y that our function will ever attain. And that value of y would be described within the range of our parabola, the range of the function. The x-coordinate p is the value at which your minimum or maximum occurs, and q is the value of that min or max. I want you to take a look at this link in Desmos to see what happens as we vary the values of p, q, and a. On this prepared sheet in Desmos, we can see the equation of the quadratic function given in vertex form. We have a slider for a, p, and q, as well as, let's label it, but we have the vertex identified. So as we change a to be positive, you can see that my parabola is stretched vertically, and therefore it looks narrower. Whereas if it ends up being a negative value, it flips and is reflected in the x-axis. Okay, so that makes it open down. The other thing we can vary is the p and q value, which change our vertex. So as I change p to be a positive value, it moves my vertex to the right along the x-axis, and if I change q to be positive or negative, it shifts the vertex vertically. So this is the same sort of transformations that we've examined with trig functions, and we're going to look more at graphing quadratic functions in the next video. But next we're going to look at how to change an equation from general form into vertex form by completing the square. Completing the square is the process to find the vertex PQ by putting the quadratic equation into vertex form. Therefore, given the quadratic equation in general form, ax squared plus bx plus c, we complete the square to put it in the form a multiplied by x minus p squared plus q. This process is described below using the following steps. First thing we do is factor out a. We only need to do so if a is not equal to 1. So we factor it out from the x terms. Step 2 is determine an additional term that we need to add or subtract from our given equation in order to make a perfect square trinomial, which can be factored as x minus b over 2a all squared. But we can't just arbitrarily add something to our equation. We must also subtract it or balance the equation in order to leave the equation as it originally was. And this step will make a lot more sense once we get to some of the examples. And one thing to remember is that if we have x plus y all squared, it is equal to x squared plus 2xy plus y squared. Okay, once we have added or subtracted our additional term as well as balanced, we can collect the constant and describe the vertex point as PQ. Now let's do some examples to determine the vertex form of a quadratic equation by completing the square and then stating the coordinates of the vertex. It's worth noting that we could have described the vertex in another fashion here. If we knew what our roots are, so say we have some x-axis and we have two roots that are given, we know that the vertex must exist halfway between the two roots because of the symmetric nature of a parabola. Therefore, if we were to find our two roots, we could find the midpoint between them, and that would be the x value of our vertex. Then we could calculate the corresponding y value by plugging that value into the original equation and describe the vertex in that fashion. So that's one way that you can check or confirm whether or not the given method of completing the square does in fact work. Okay, the first question we have is f of x is equal to x squared minus 6x plus 5. Note that the coefficient of x squared, which we call a, is equal to 1. Therefore, we don't need to complete the first step of our steps above. What we want to do is complete the square by taking a look at the x term. So we have x squared minus 6x, and we need to determine what do I need to add or subtract from x squared minus 6x in order to make it a perfect square. Okay, therefore, we have x squared minus 6x, and we want to figure out what we must add or subtract. Then we have plus 5. So in order to make x squared minus 6x a perfect square, we must add 9 to it. To determine the value that we must add to the equation to make it a perfect square, we take our middle value, so negative 6, we divide it by 2, and then square it. So that gives us minus 3 squared, which is equal to 9. Okay, now we've added this 9 into the equation. You can still see here I have my original value of 5 at the end. We can't just arbitrarily add 9 to the quadratic equation. We must also subtract 9 in order to balance it. Okay, what this does is allows us to create a perfect square with x squared minus 6x plus 9. And now we can write this as x minus 3 all squared. So I've factored my perfect square, and then we combine the constant terms, so minus 4 and plus 5, to be negative 4. One thing you can do after completing the square is expand out your vertex form and simplify it, and you should get the equation that you started with if you completed the steps properly. Okay, now that we have the equation in vertex form, we can identify the vertex of the parabola. Remember that the x-coordinate of your vertex will be the opposite sign of what is inside your equation here. So our vertex will have an x-coordinate of positive 3 and a y-coordinate of negative 4. Therefore, the vertex is positive 3, negative 4. Looking at part B, we have 2x squared plus 4x plus 1. We want to determine the coordinates of the vertex by completing the square and putting the given equation in vertex form. Step 1 is to factor the a value out of the x terms. You can see the a value is 2. Therefore, when we factor it out, you're left with x squared plus 2x plus 1. Now we want to complete the square. So create a perfect square trinomial, and we have x squared plus 2x. And in order to complete the square, we must take the middle term of 2, divide it in half, and square it. And that gives us a value of 1 that we're adding into the equation. Don't forget we still have the plus 1 from the original equation. And in order to balance this, we've added in 1, but it also has a coefficient of positive 2. Therefore, to balance this equation, we must subtract 2 times 1. And remember that 2 comes from the fact that our coefficient of 2 is 2, and then we have the 1 that we've added in. Now we have a perfect square trinomial that we can factor. We have 2 times x plus 1 squared, and then we are subtracting 2 and adding 1, therefore we're left with negative 1. And we can identify the vertex as being negative 1, negative 1. It's worth taking the time to graph out the parabola that was given. So the equation, we have 2x squared plus 4x plus 1, and we could use Desmos to do so. When we graph this, we can identify our vertex as being negative 1, negative 1. So that's one way that you can check your work. You can also take the vertex form of the equation that you found, expand it all out, and check that it equals the original. Now in a third, slightly more complicated coefficient example, we're going to complete the square again. So first thing we do is we factor out that 3/4, and we get 3 over 4, and what is remaining is x squared minus 8 over 9x plus 1 over 26 outside of the bracket. So we don't factor the 3/4 out of that constant. Just as a reminder, in order to arrive at the negative 8 over 9, we took negative 2/3 and divided 3/4. You can confirm if this is correct by expanding the 3/4 back into the brackets, multiplying the fractions, and simplifying, and you'll get back to negative 2/3. Okay, now we must figure out how to make this a perfect square trinomial. So what do we need to add in there? We have x squared minus 8 over 9x. We must add something in, balance it out again, and then add the 1 over 26. To figure out what we need to add in, we take the 8 over 9 minus 8 over 9, divide it by 2, and then square it. Okay, what this ends up giving us is negative 4 over 9 squared, which can be written as 16 over 81. So that's what we're going to add in, 16 over 81. We must balance the equation. Don't forget about this coefficient of 3/4. Because we added 16 over 81, we must subtract 3/4 times 16 over 81. Now factoring our perfect square trinomial, we get x minus 4 over 9 squared, and we simplify everything outside of the brackets, and we get minus 77 over 702. So you could evaluate that portion outside of the brackets using the fraction key on your calculator, or by finding a common denominator and combining the fractions. So this tells us that we have a vertex at 4 over 9 negative 77 over 702, or expressed rounded to two significant figures, we can write this as 0.44 and negative 0.11, which would allow you to approximate the vertex and graph it correctly. In the next video, we're going to look at graphing quadratic equations. Given everything that we've learned so far in these videos, we know how to determine the roots as well as the vertex of a quadratic function. Next, we'll be looking at different transformations.